Mr. Strauss's chemistry class is filmed before a live studio audience. No laugh track was used at all during this class, and no pickles were at all hurt at any point during this lecture. So, Bohr model. A couple of things that were good about the Bohr model is it explained the spectral lines. So we know that hydrogen gives off red, green, blue, and purple light. And the Bohr model explained how that happens. When the electrons fall, they produce those light. When it falls from the third to the second, you get red. Fourth to the second, green. Fifth to the second, blue. And sixth to the second, you get purple light. So there are some good things about the Bohr model, but there are also some inconsistencies. First of all, it did not explain why negative electrons don't get attracted to the positive protons in the nucleus, and why don't those then electrons spin into the nucleus? Because if they have opposite charges, they should be attracted to each other. Another problem with the Bohr model is that he didn't explain why the orbits are quantized. He just said that they were. And then the other problem with the Bohr model is that he didn't explain the Summerfeld and the Zeeman effect. Now, the Summerfeld effect was that when Summerfeld built a really good spectroscope, they realized that some of these lines were not actually single lines at all. They were multiple lines. So the first line, the red line, stayed as a single line. But the green line split into two lines. The first line was very thin, and the second line was a little bit thicker. Now, if you want to use colored pens and pencils, you can, but you really don't have to. You can just use a regular old pencil and just draw the number of lines. The blue line was not a single line either, Kyle. It was actually 3 lines. One thin one fatter one, and one even fatter. And so how many lines do you think the purple one was made up of?
4.
4. Yep. So first one was thin, second one was a little thicker, even thicker, and even thicker. So in science, let's see, when you have an observation, you come up with some way to describe your observation. And sometimes it's kind of nonsensical. Okay, so like when J.J. Thomson discovered the electron, he wanted to call it the corpuscle. It was outvoted, and it was called the electron. When they discovered the quarks, quarks are named after a made-up word from James Joyce's novel Finnegan's Wake, quarks. And then the names of them: top, bottom, strange, charm, up and down. And they actually wanted to name strange and charm truth and beauty. So they have some strange names when you're first starting off. And no different here with these lines. They called the first line sharp. So the very thin line they called sharp. The next line they called principal. The third line in the sequence they called diffuse. And the fourth line in the sequence they called fine. So the red line stayed a single line, the green line split into 2, the blue line split into SPD, the fourth line split into SPD and F. And when you applied a magnet to it, the S line always stayed as a single line. But the P line always split into three. So the S line always stayed as a single line, but the P line split into three. And the D line split into 5. So the S line always stayed a single line, the P split into 3, the D split into 5, and what do you think happened to the F line? 7. And then scientists, Logan, look for patterns, right? So 1, 1, 3, 1, 3, 5, 1, 3, 5, 7. And the total number of lines here, Shannon, are 1, 4, 9, 16. So what's that pattern there? Perfect squares. So if you take 1 squared, you get 1. If you take 2 squared, you get 4. If you take 3 squared, you get 9. You get 4 squared, you get 16. So now the question is to explain why this pattern occurs. So this takes us then to 1924, Victor de Broglie. De Broglie was studying the electron, just like a lot of these other guys at this time. And de Broglie was looking at Planck's work. And remember, Max Planck said that light, which is a wave, could be treated like a particle. You could pretend that light was like a bunch of little BBs flying through the air into your eye. But of course, you know, that seems silly, right? I mean, little BBs flying through the air into your eye, I mean, wouldn't that hurt? And Millikan and Thomson had just got done measuring the mass of the electron. It's a small mass, 9.1 times 10 to the negative 28 grams there, Delaney, but it does have mass. So a baseball has mass. You can envision a baseball flying through the air. The electron is no different. The only thing is the mass is tinier. And there's that little electron flying through the air. But de Broglie said, well, wait a minute. If Max Planck can say a wave can act like a particle, light can act like a little particle called a photon, why can't we do the opposite? Why can't we take a tiny electron and pretend that it's a wave? Okay? So that's what de Broglie suggested. We're not done. And scientists set out to prove this, or disprove this. And it's called the single slit and the double slit experiment. So I'm going to take an electron gun, and I'm going to shoot electrons at a wall. But I'm going to put a hole in the wall, a slit, an opening. And on the other side of the wall, I'll put a target. So what's going to happen here, Pat, if the electron is a little particle, like a bullet? Where will the electrons hit? Target. Where on the target?
Where the slit is.
Where the slit is. So right there in the center. Will any electrons hit up here? No. Any down there? No. Should have. But what if the electron is a wave like de Broglie is suggesting? If the electron is a wave, waves spread out, right? And what's going to happen when it hits the wall? It'll go through, and then what will happen to your wave? It'll spread out, and then where will it hit the wall? Everywhere. So this seems like a pretty simple experiment, Harry, to test whether or not the electron is a wave. Shoot your electrons out. If they hit just in the center, then you know the electron is a particle. If the electron hits everywhere, then it must be a wave. So here are the results of the single slit experiment. Ready? So they shot some electrons at it. After 28 electrons, you can see that little pattern right there. What does that look like to you? Does that look like a wave hitting?
Yeah.
Or does that look like bullets hitting a target?
Well, they're not all in the center.
They're not all in the center, but where are most of them?
Towards the middle.
Towards the middle. So after 28 electrons, that sure looks to me like the electron is a little particle and they're all kind of hitting in the center. I'm not sure why those were off to the side. But let's keep going. After 1,000 electrons. After 10,000 electrons. After 1,000,000 electrons. Now when you look at it, did some electrons hit off to the sides? Yeah. Where did the electrons hit the most? In the middle. So that looks like a wave pattern. There are electrons hitting everywhere. Where do they hit with the greatest intensity? In the middle, just like a wave, right? The height of a wave is always the biggest in the middle. You know this, Logan, from jumping waves at the beach. Remember? You go down on the beach, the waves come in, and you jump the waves. Where's the wave highest? In the middle. That's where the most fun is. That's where the wave is the highest. You get a little scared, you go off to the side, and you jump over the little part of the wave. Okay? So the wave is the strongest in the middle. So now we're kind of stuck with a little bit of a dilemma here. How is it the electron is both a particle and a wave? How is it appearing to be both? Well, let's do another experiment. Let's do a double slit. Now this time, I'm going to shoot it at the wall, but this time I'm going to put 2 slits. If I do this, if the electron is a particle, will any electrons get through?
No.
No, because it's just going to hit the wall. Nothing should get through. If the electron is a wave, then what's going to happen? But they'll go through both openings, right? And not only will they go through both openings, they'll go through both openings simultaneously. I'll come back to this in a second to really make you confused, Alexa. The wave is going out, and it will go through both holes simultaneously, okay? And then on the other side, they'll spread out and they'll interfere. So what does this turn out to be? This is what actually happens. You do end up with a wave interference with the greatest intensity in the middle. So this is another example that the electron behaves like a wave. But this is troublesome because if the electron is behaving like a wave, how does it go through both openings simultaneously? Because it's got mass, right? How does something that has mass, how does it spread out? How does something that has mass go through 2 openings at the same time? Okay, just to give you an analogy to show you how strange this is, Shannon. Imagine that we threw a person towards that opening. They just bounce across. They hit it and stop. But if you're an electron, what you're saying is you rip apart, you go through both openings at the same time, and you rejoin on the other side? How can an electron, which is supposed to be this tiny little baseball weighing 9.1 times 10 to the negative 28, how can it go through 2 places at the same time? Because that's what it's saying, is that the electron can be in 2 places at the same time. And it can behave as either a particle or a wave. And I guess the way they kind of look at it is that it's both. And you decide, the experimenter decides which one it is. And that's another strange thing about quantum mechanics. If you want the electron to look like a particle alley, then it's a particle. If you want the electron to look like a wave, then it's a wave. In other words, the experimenter determines the outcome of the results. You, as the experimenter, affect the outcome. If Yuki wants to see the electron as a particle, then it's a particle. But if Logan wants to see it as a wave, then it's a wave. And I know there's 2 minutes left, but I want you guys to stick with me. Here is an analogy. What is this a picture of?
A lady.
Who sees an old lady?
Oh, you turn it upside down.
Who sees a young woman? Who thinks the electron's a wave? Who thinks it's a particle? It's both. Just like this is a picture of both.
What? How is it?
The old lady, there's her chin, there's her mouth,
What? That's
There's
so
her
weird.
eye. That's her big nose.
Oh my god, it's so weird. Wait, now I like don't see the young lady. I can't see the old lady.
The old lady, that's her eye, that's her nose, that's her mouth, that's her chin. And the old lady's kind of down like this, going. Alright? Now the young lady, she is turned away. That's her chin, that's her little coquette nose, and her eyelash and her ear. So the young lady, she's turned away like this. Alright? But who determines what you see? You do. You determine what you see, just like the electron. And so this ends another session of Mr. Strauss's chemistry class. To our Polish viewers, jak się masz?
Film in our class every day, Strauss.